And also we go to the second part of this lecture, and and so we were talking about basic theorems on limits, and so the third theorem we introduce is the so-called double comparison or sandwich, or in Italian due carabinieri. So this is a very useful result that we will use extensively in the following. So, theorem. The name is double comparison. Or sandwich. Or in Italian, the two carabinieri. You know, the carabinieri is an old corps of Italian army. They started as being at the service of the king of Italy. Now we do no longer have a king, we have a republic, but there's a special structure of carabinieri remained. And so the theorem is the following. So you're given three real sequences. Let us call them xn, yn, zn, such that yn goes to L, which is a real number, and also Zn converges to the same limit L. Moreover, you know that xn is included between yn and zn. So the message is that the lower bound sequence, lower bound yn goes to L, the sequence upper bound zn goes to L too, therefore also the sequence in the middle goes to L. This is the meaning of the sandwich. Xn is like the ham or whatever is inside the sandwich, I don't know, the salad. And it is compressed between the two slices of bread. This is why we call it sandwich theorem. And two carabinieri, this is why xn is the thief or the killer or whatever has to be captured, and in order to bring it to the prison, it is better to use two carabinieri, and they go to the same place, which is the prison, the limit L. So also the guilty guy, xn, will go to the prison. Okay? This is the meaning of the name. The idea is quite simple, and also the proof is extremely simple. So the proof is the following. Let epsilon larger than 0 be an arbitrary number. And now we just apply the definition of limit. So since the sequence yn tends to L, we know that there is a natural number n1 bar such that whenever n is larger than n bar 1, then yn lies between L minus epsilon and L plus epsilon. Eventually, remember the definition of limit, eventually yn is at a distance from the limit L that is smaller than epsilon. So, analogously, since the other sequence Zn goes to L, then there exists n2 in n such that for n larger than n bar 2 in n, we have that Zn lies at a distance between L plus L minus epsilon, sorry, at a distance which is less than epsilon from the limit L. Okay, this is the meaning of this writing. Now the situation is very simple, and we can look at it pictorially. So here you have the limit L, and here you have L minus epsilon and L plus epsilon. And here inside this interval fall both sequences yn and zn. Now, since xn is included between the two, also xn must be in the same interval made of all numbers whose distance from L is less than epsilon. But in order to do that, in order to state this conclusion, we have to ensure that these two conditions, 1 and 2, hold together simultaneously. And how can we do? Perhaps now you are able to have an intuition of what happens. In order to make these two conditions hold eventually, we must use n, which is larger simultaneously than n bar 1 and n bar 2. So to this purpose, and only to this purpose, we define n bar as the maximum of n bar 1 and n bar 2. Therefore, whenever n is larger than n bar, we have that n larger than n bar 1 and n larger than n bar 2. Therefore, conditions, let me call them 1 and 2, hold simultaneously. One and 2 are these two conditions here. This is 1, this is 2. So, we end up with, we know that L minus epsilon is less than yn, but now we use the sandwich hypothesis. We use this hypothesis here, which is really the core of the theorem. So yn is less or equal xn, which is less or equal zn, that, according to inequality 2, is strictly less than L plus epsilon. Here we have a chain of inequality, and of this chain of inequality we keep this part, L minus epsilon, strictly less than xn, strictly less than L plus epsilon. So we prove that there exists an n bar such that whenever n is larger than n bar, we have that xn is included between L minus epsilon and L plus epsilon, which means that xn lies at a distance from L less than epsilon. So the conclusion is that by definition of limit, we conclude xn goes to L. This is the end. Okay? We will use this statement a lot, and I just put here a remark that says the following: this theorem, like every other theorem on limits of sequences, holds even in the case that the hypotheses are verified only eventually. Only eventually. Why? Because so in the definition of limit, eventually is included when we say that there exists an n bar. So think a bit of it, and an example of use of this theorem can be the following. Prove that 1, the sequence 1 over n plus 1 goes to 0. Okay, we can do it directly. Like as usual, take epsilon larger than 0 and so on. But we can do it directly, but this time we use the comparison, the double comparison theorem. And we start by observing that eventually one has n which is less than n plus 1, and this is obvious, this is absolutely trivial. This is less than n squared. Okay? This holds only eventually, and let me, this holds eventually, since if we consider the inequality n squared minus n squared plus 1, sorry, minus n squared minus 1 larger than 0, which is nothing by this guy here, sorry, n squared minus n minus 1. Okay, here we compute the two roots of this second degree equation, algebraic equation. So we have n 1 2, this is equal to 1 plus minus 1 plus 4 divided by 2, and this is 1 plus square root of 5 divided by 2. This is a very famous number. However, we have to say that if n is larger than 1 plus, sorry, plus or minus 1, but minus is meaningless here because 1 minus square root of 5 is a negative number. So we are talking about natural numbers, so they are non-negative, and larger than 1 plus square root of 5 divided by 2. And if this is true, then the second inequality in let me call it asterisk, is verified. Okay, this number here, 1 plus square root of 5 divided by 2, is less than 2. Because the square root of 5 is less than 3. Okay? So, asterisk holds for every n larger or equal than 2. Okay? So now we reverse asterisk. So we pass from these numbers to their inverses with respect to the product. And when doing that, we have to reverse the inequalities. So we have 1 over n squared less than 1 over n plus 1 less than 1 over n. Now remember that we proved directly by taking epsilon and finding the n bar, we found that 1 over n goes to 0. Then as an exercise, I left you that 1 over n to whatever power, whatever positive power alpha, this goes to 0. And then from the two Carabinieri theorems, we have that also this goes to 0 from double comparison. Moreover, of course, we can extend this observation, but as a remark, we can immediately show that if P of n is something like sum for j going from 0 to capital N, and here we have aj n to the j's power equal to a naught plus a1 n plus a2 n squared plus dots 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 an n to the capital nth power. So, which means that is a polynomial in n of degree capital N, which means that in particular these a0, a1, these are real numbers, coefficients. So when you consider a polynomial in n, then you have that the sequence made of the inverse of a polynomial always goes to 0. As an exercise, you can try to prove it. By using double comparison. Okay. And again, another exercise. Try to prove the sequence e to the minus n goes to 0. Then the next observation is that since there is double comparison, there must be a simple comparison. Okay, this is very simple. Sometimes I don't tell this in the lecture because it is quite obvious, but this year, since the communications is quite different, I prefer to give you this as a remark. And this is a simple or one side comparison. Which is the following. Which is the following. So consider two sequences. So you have an and bn, real sequences, real convergent sequences. So you have that an tends to L, Bn tends to K, and moreover, An is less or equal Bn. Then we have that L is less or equal K. Okay, you can try to prove it. And so it is simpler if we use the next argument, which is called the algebra of limits. The following topics. Okay, which is the following: algebra of limits. The question to which the algebra of limit answer is the following: what happens if I consider the sum of convergent sequence or the product of convergent sequence of or things like that? Okay, so the question is, so what is the behavior, the asymptotic behavior of the sum, the product, and the ratio of two convergent sequences? Are they still convergent? And if so, what is their limit? We will see that the answer is the simplest one. We start from the sum. So first theorem, which is the sum. We have two convergent sequences. An converges to L, which is real number. Bn converges to K, which is a real number too. Then the sequence Cn, which is defined as the sum of An plus Bn, converges to L plus K. By the way, I use this notation when it is a definition: 2 points, 2 dots, and equal sign. Okay? And this is what is sometimes expressed like the limit of a sum, of the sum of two sequences is the sum of the limits. This is why I told you the algebra of limits is extremely simple. Don't believe that all algebras are like that. Algebra of derivatives is not like that. It is the same for the sum, but it is not the same for the product, for instance. However, proof. And now we start with a schema which is always the same. We have to use the definition, so the definition needs an epsilon, and to show that eventually the sequence Cn lies from the number L plus K to a distance which is less than epsilon. So the starting point is always this statement: let epsilon larger than 0 be an arbitrary number. Okay? Then, since the sequence An goes to L, then there exists n bar 1 such that for n larger than n bar 1, An minus L is less than epsilon over 2. This is a small surprise. Why don't I use epsilon? We will see at the end of the proof. It's just an aesthetic point. It is not really conceptually interesting. But is it correct to say epsilon over 2? Yes, because the definition says that eventually the sequence is far from the limit less than any positive number. So I choose epsilon, but then the n1 bar I'm interested in is not the one related to epsilon, but to another positive number, which is epsilon over 2. So the definition is respected. Okay? Think of it if you don't agree. So, in a completely analogous way, we have that since Bn tends to k, then there exists n bar 2 such that after n bar 2, whenever n is larger than n bar 2, then Bn minus k is less than epsilon over 2. Now we want these two relationships hold together. How can we do? As usual, we define n bar as being the maximum between n bar 1 and n bar 2. And now take n larger than n bar. So since n is larger than n bar, then it will be larger than n bar 1 and then n bar 2. So these two relationships hold together. And now let's go with a final computation that consists in evaluating the distance between the sequence Cn, which is the sum of An and Bn, and the sum of the two limits, L plus K. First, we just apply the definition of Cn. Cn is An plus Bn, then minus L minus K. Now, commutative property of the sum, An we can move minus L here, plus Bn we can move minus K here. Okay? Now, we consider it as being between parentheses, so we use the associative property, and now we split the absolute value and use the first triangular inequality. So here we have An minus L plus Bn minus K. And now we recall that the two inequalities here hold together. So here we have this is less than epsilon over 2 plus epsilon over 2, which is less than epsilon. So what we proved now, we just proved that for every epsilon, here there is arbitrary, so for every epsilon larger than 0, there exists a natural index n bar such that after n bar, which means eventually, the distance between the sequence Cn and the number L plus K is less than epsilon. And here it is just a matter of applying definition of limit by applying the definition of limit. We end up with Cn that converges to L plus K, and this is the end of the proof. The limit of the sum is the sum of the limit. Now I stop this recording here.